I'm Mike Schnecker. Many applications, such as radar systems, involve the measurement of pulsed RF carriers. But in addition to radar systems, there's many other applications, such as keyless entry and even pulsed radios, where the envelope of an RF pulse carrier needs to be measured. The analysis of this type of signal is enhanced using a high-speed oscilloscope, such as the Rohde and Schwarz Rtp. Here we have a Rohde and Schwarz Rtp 084. It's an 8 gigahertz bandwidth 4-channel oscilloscope with very deep memory, very fast update rate of up to 1 million waveforms per second, and an advanced digital trigger. All these features enable the measurement of pulsed RF signals very accurately with very powerful analysis tools. We're looking at a signal being generated by a Rohde and Schwarz SMW200A signal generator. And this generator is a vector signal generator capable of generating a broad variety of RF signals with different modulations. We're going to use a simple pulsed RF mode here. So that pulsed RF carrier at 2.8 gigahertz is being applied to the input of the RTP oscilloscope. And we're measuring the waveform here on the screen. The upper grid is the actual RF pulse, which you can see as sort of a yellow band of signal. That's the RF carrier being captured at RF. And because we want to measure the envelope of this carrier, such as rise time and fall time and pulse width, we're going to use a math function to detect the envelope of the RF carrier. And so that math function was set up here as math number 1, and that's shown with the blue readout and the blue trace shown here zoomed in. So we're zoomed in on the rising edge of that RF pulse. And so you can see the detected envelope in blue and the RF carrier in yellow. To make it easier to see, I'm going to minimize the RF waveform. And when I do that, it puts the RF waveform in the box here on the right. And now you can clearly see the detected envelope. We're looking at the rise time here, and the overall pulse is in the upper display. Now, if I increase the time per division, I can actually see more pulses on the screen. So as I go up in a larger time per division setting, you can start to see consecutive pulses out of the radar. So there's one pulse, there's the other pulse, and there's a pair of pulses shown again in the RF as well. So we can capture multiple pulses on a single screen. Therefore, for example, measuring the fact that it is in fact repeating, and you can get the interpulse period measured pretty well that way as well. One of the key things about being able to measure pulsed RF signals is that you need to be able to trigger reliably on them. So one of the key elements of triggering is being able to trigger not on the RF carrier, but on the pulse envelope. And we do this using our digital triggering system. And I'm just going to give a quick view of what we're doing. We're using a pulse width trigger. So we're triggering on the gap between 2 of the consecutive RF pulses. And in this case, we said look for a gap that's longer than 100 nanoseconds. That'll guarantee us getting the interpulse period captured, and so we can reliably trigger on the rising part of the RF signal. The digital trigger enables this to be very stable and very repeatable, which helps in the measurement process of the envelopes. Now down here, we're actually doing a set of measurements on that envelope, and they're parked on the left or right-hand side. I'm going to pull them out onto the screen and set them down there on the bottom so you can see. And we basically have a number of measurements, including rise time, fall time, positive overshoot, and pulse width, as well as the RF frequency of the carrier. And we're doing this on every pulse that's being captured by the instrument. Now, one of the key features of measuring RF pulses is being able to measure the signal on a pulse-to-pulse basis. That is, I want to see how, for example, one of the parameters, such as pulse width or amplitude, might vary on consecutive pulses. In order to do this, you need a very fast acquisition system in the instrument, one that's able to re-trigger very fast so we can capture pulses which can often be very closely spaced. The Rohde and Schwarz Rtp features the fastest acquisition system in its class. This enables us to capture consecutive acquisitions as close as 300 nanoseconds apart. So that means I could capture consecutive pulses out of a radar that are spaced as closely as 300 nanoseconds. And that's very fast pulse repetition frequency if you're thinking in terms of radar. The way we do this is using our memory feature in the instrument. So I'm going to set that up right now. But first I want to set up the measurement trend of what I want to see. So in this example, I think what I'll do is measure the pulse amplitude over time. So I'm going to select my measurement, and I'm going to select result analysis, and I'm going to enable the long-term trend. And this enables me to display a measurement over multiple acquisitions and show the trend versus time. And in here we selected high, the amplitude level of the pulse. And so you can see here this new trace that's been added to the display. That is the trend over time. Now, right now, we're just collecting a measurement every time the instrument updates. We're not capturing every consecutive pulse here because there's some processing time involved in doing the math waveform and that sort of thing. So what I'm going to do is switch over to the memory, the history mode, and capture consecutive pulses. And to do that, I'll go in the horizontal setup, and I'm going to select fast segmentation. This is a feature that allows you to store in memory a number of consecutive acquisitions. And so I'm just going to enable that. And by enabling that, I'm going to capture up to 18,000 consecutive frames and store them in memory before I update. So I set that up, and I'm just going to fire off a single acquisition, and it's filling the memory. So now it's done filling the memory. It took, I guess, seems like less than a second. And if we look in here, we can see on the top here that there is a history that's stored. And we have about 18,000 waveforms. And right now, the instrument is sort of playing those waveforms back. So what you see on the screen here is that history of waveforms in memory being played back and the measurements being tracked on the screen. And we're looking at the variation of the pulse amplitude on a pulse-to-pulse basis. And if you look closely at this history, and when it's finished playing, you'll notice that we've captured about 2 seconds worth of consecutive data. So it's 2 seconds worth of pulses, each pulse captured consecutively. And we're measuring the variation in the amplitude from pulse to pulse. This is an example of the kinds of measurements you can do on pulsed RF signals. These are the kinds of things that engineers need to analyze in these applications. I hope this was a helpful video, and look forward to doing some more of these.